Hey guys, what's up? Welcome back to the channel, or if you're new here, welcome. Today we're diving into something that sounds a bit technical, but it's actually super important and pretty cool once you get the hang of it. So yeah, let's get started. So we're gonna be going over interrupts. So first things first, what even are interrupts? So in computer systems, an interrupt is like a little tap on the shoulder for the CPU. Imagine you're working on homework and someone texts you. That text is an interrupt. It grabs your attention and makes you stop what you're doing to check it. In computers, interrupts signal the CPU that something important needs its attention. Maybe a hardware device needs a service or a program hit an error. There are three main types. So there are hardware interrupts. These come from physical devices like your keyboard sending a signal when you press a key or your mouse clicking on something. There are also software interrupts. Um, Software interrupts. These come from programs when they need the OS to do something on their behalf, like system calls and exceptions. So these happen when something goes wrong, like division by zero or invalid memory access. Think of them like the CPU saying, "Oh, something's not right here," and then it just takes action. Um, so why do we need interrupts? So they keep our systems responsive and efficient. Without them, your computer would have to keep checking if something needs its attention. It's like asking, "Are we there yet?" over and over every 5 minutes. Interrupts let it focus on tasks and only stop when something actually important happens. Okay, so how does an OS actually handle an interrupt? It's a whole process. So number one, the first step is an interrupt occurs. A device or program signals for attention. Number two, a CPU pauses. The current task stops, but not before saving its state, so it can pick up where it left off after. Number three, it identifies an interrupt. The OS figures out what caused the interruption. And number four, it executes the ISR. So the interrupt service routine, or the ISR, jumps in to handle the situation. And then number five, it resumes. So once the ISR finishes, the CPU goes back to doing what it was doing, like nothing ever happened. So now, not all interrupts are equally important. Some need immediate attention, like hardware failures, while others can wait a bit. That's where interrupt prioritization comes in. So high priority interrupts jump the line and get handled first. Without prioritization, your computer could easily lag or crash if it gets overwhelmed. Operating systems use different techniques to manage and prioritize interrupts. They use interrupt controllers. We'll cover those in a bit. And they sometimes even mask lower priority interrupts until the important stuff is done. So ISRs, which are interrupt service routines. So what's an ISR? It's the code that actually deals with an interrupt. So when interrupt happens, the ISR steps in, fixes the issue, and then lets the CPU get back to work. Think of it like a fire drill. When the alarm goes off, the ISR is the teacher making sure everyone gets out safely. The structure of an ISR is pretty straightforward. It identifies the interrupt source, and then handles the requested action, and then clears the interrupted signal, and then restores the CPU state. So you can actually see the diagram here, basically just uh, demonstrating what I just explained. So it identifies the interrupt source, goes over, handles the requested action, clears the interrupt signal, and then restores the CPU state, and then goes back to the user program. Um, but here's the tricky part. So essentially, let me see. Writing good ISRs is hard. Why? So timing. ISRs need to be fast. If they take too long, they delay other processes and the system becomes unresponsive. Another thing is concurrency. So multiple interrupts can happen at once, and ISRs need to avoid conflicts. Another thing would be reentrancy. So ISRs should be able to run independently without interfering with each other. Another thing would be resource management. Accessing shared resources without causing deadlock or data corruption is a huge challenge. And another thing is stack space. So ISRs have limited stack space, so they need to use memory efficiently. But good ISRs are like good emergency responders. They're quick, efficient, and ready for anything. And then we're gonna go over the role of interrupt controllers. So how do we keep track of all these interrupts? So that's the job of the interrupt controllers. These devices manage multiple interrupt signals and decide which ones get passed on to the CPU and in what order. There are different architectures for interrupt controllers. There's programmable interrupt controllers, or PICs. These are older, but they're still used in some systems. And there's also advanced programmable interrupt controllers. or APICs. They're more advanced and handles multiple processors. And there's also message signal interrupts or MSIs. These are used in newer systems for more efficient signaling. Now, how do they help with efficient handling? Um, so prioritization, they decide which interrupt gets handled first, and there's also a thing called interrupt masking. So these can temporarily block lower priority interrupts, so more urgent ones can get through. And then there's also load balancing, which in multi-core systems they distribute interrupts across different CPUs to avoid overloading one core. And also efficient routing, so they send interrupts directly to the most appropriate processor, reducing latency. In modern systems, this makes sure that high performance tasks run smoothly even when a lot of things are happening at once. So let's talk strategy. How do we handle interrupts efficiently? There are two main approaches. There's polling. So in this instance, the CPU keeps checking devices to see if they need attention. It's simple, but it wastes a lot of processing time. And there's also interrupt-driven input-output. So devices signal the CPU only when they need something. This saves resources and keeps the systems responsive. So there's going to be some advantages and disadvantages to both strategies. So for polling, it's simple and predictable, but it's also inefficient and wasteful of CPU time. And then for interrupt driven, it's efficient and responsive, but it's more complex and requires good prioritization. So most modern systems are usually interrupt driven because it's way more efficient, but they still sometimes use polling for simple or real time tasks. So where do we see interrupts in the real world? We basically see them everywhere. We see them in device drivers like your mouse, your keyboard, printers. They all use interrupts to communicate with the OS. We see them in networking. Receiving and sending data packets relies heavily on interrupt-driven input-output. Um, Multitasking interrupts let your OS switch between applications smoothly. So if you're like, studying and like using like I don't know like Canvas or Blackboard, and you want to go switch a song on like Spotify, it makes sure that that process goes really smoothly. And then also for real time systems, so think medical services and automotive systems. Fast response times are very critical for these systems, so it just ensures that everything is happening very smoothly. In terms of real world OS examples, there's for Linux, Linux uses advanced interrupt handling with APIC and MSI support. Windows implements deferred procedural calls or DPCs for low latency handling, and Mac OS uses a hybrid approach for efficient device management. So let's take a closer look at Linux. It's known for its efficient and scalable interrupt handling. Some of its standout features include soft IRQs and tasklets. These separate lower priority work from immediate ISR tasks. There's also Linux also uses bottom halves. Uh, these uh, these bottom halves they defer the work after the ISR finishes to avoid blocking other interrupts. Linux also uses IQR affinity. These assign specific interrupts to certain CPU cores for better load balancing, and it also uses preemptive kernel. It ensures low latency responses even when handling multiple processes. So these optimizations make Linux perfect for everything from servers to embedded systems. So even with all these advancements, there are still challenges. So one of these challenges would include latency, so minimizing the time between an interrupt and its handling, scalability, keeping performance high with multi-core and multi-threaded systems, and security, preventing malicious use of interrupts for attacks like buffer overflows. Um, so future solutions could include AI-driven prioritization. So AI could help in helping like a smarter interrupt management, hardware innovations. These can be created to create a more faster and more efficient controllers. And then for the kernel design, it can just overall improve. This would allow for more flexible and scalable architectures. Um, but basically, that was a brief overview of interrupts. They keep everything running smoothly and make modern computing possible. If you found this helpful, hit that like button, subscribe for more tech content, and let me know in the comments if you want me to cover any other topics. But yeah, thanks for watching. Bye.